Can you see the screen?
Yes, doctor.
Yes. Yes, we can.
Okay. Okay, so what we were discussing in the previous lecture was how to eliminate certain harmonics from the output voltage, because the output voltage is in the form of a square wave. It is like a square wave. It is like a square wave, and if you take the Fourier of this, then we see that it has fundamental component plus harmonics, and the harmonics are like one third harmonic, fifth harmonics, and so on. So it is, and the magnitude is like V1 by 3, V1 by 5, V1 by 7 in this order. Now, if you want to eliminate third harmonic, we have to switch the inverter in such a way that the switching angle is 30 degree. For fifth harmonic elimination, it will be 45 degree. No, 18 degree, sorry. 18 degree, and so on. So, and the magnitude of the nth harmonic is given like this, where you see this 4 VDC by pi is V1. This is fundamental. This is fundamental. And nth harmonic you can write as this. Now, if you are switching at certain angle, you have to put cos alpha. So this is fundamental, and this is nth harmonics. And the harmonic magnitude that varies with the angle is shown in this graph. Now, this is a problem. It says that design an inverter that supply a series RL load with a of the previous example, where the load is 10 ohm and 25 millihenry with the fundamental frequency current component of 9.27 ampere, but with a total harmonic distortion of less than 10%. So total harmonic distortion in the case of a square wave is calculated here. So this is, in this example, we have calculated the total harmonic distortion. The total harmonic distortion in a voltage waveform is given by this relation. Total harmonic distortion is given as square root of Vrms square minus V fundamental RMS square divided by V1 RMS and multiplied by 100%, and that gives you the total harmonic distortion in the voltage waveform. Okay, remember, this is the fundamental, and this is like full wave, whatever it is, like square wave or any other kind of wave. This is the RMS value you have to consider for the whole waveform, and here you have to consider only for the fundamental. So for the square waveform output, for the square output, it is fixed value, which is 48.3%. And in the current harmonics, total harmonic distortion is given as IN RMS square under root over I1 RMS. Now here you see N varies from 2, so it is not 1. So the fundamental is in the denominator. So this is like, I third harmonic, I fifth harmonic, I seventh harmonic, I ninth harmonics RMS values divided by the fundamental RMS values, and this comes out as 16.7%. So this is the total harmonic distortion in the current. This is the total harmonic distortion in the voltage in the case of a square wave. Now, in this question, it is asked to reduce the current total harmonic distortion to 10%, less than 10%. So this is our goal, to achieve a total harmonic distortion in current less than 10%. So how we can achieve this? We can achieve this by eliminating the harmonics from the waveform, and the strongest harmonic in a waveform is third harmonic. So we will eliminate third harmonic. So to eliminate third harmonic, what should be the switching angle? The switching angle should be 30 degree. And what will be the fundamental voltage? This is peak. Fundamental peak is 4 VDC by pi into cos alpha. And we know this. Hello? Can you hear me?
Yes, doctor.
Yes, doctor.
There is
Can hear you.
some noise. I don't know why. There is echo in the sound. I just leave and come back again, okay? Okay, this is now okay, I think. You can hear me now?
Yes, we can hear you.
Okay, I don't know what was the issue. Okay. Now, you see, if we put alpha is equal to 30 degree, then we will be able to eliminate third harmonic. The third harmonic component, V3, will be equal to 0. Okay. So, one element will be 0. So, then we will check what will be the total harmonic distortion in current. So, we have to calculate current for the fundamental, then third, fifth, seventh, ninth, like this. So, what is VDC? The DC link voltage is not given here. This is not given here. So, the fundamental voltage is I1 into Z1. The fundamental current is given as 9.27, and the impedance are given 10 and 25 millihenry. So, with this, we can calculate what is the fundamental peak. This is fundamental peak 127 volt. So now with this fundamental peak, we know this fundamental formula, then we can calculate what should be the DC link voltage. So we see that the DC link voltage should be 116 volt. What is the DC link voltage? This is my inverter. So input is VDC and the output is AC. So this DC link voltage we calculated as 116, corresponding to 30 degree switching of the output voltage waveform, and the fundamental voltage of 127 volt peak. The DC link voltage should be equal to 116 volt. Now with this, we will now calculate the RMS currents so that we can calculate the total harmonic distortion. So for the fundamental value, when n is equal to 1, the frequency given is 60 hertz. The fundamental voltage is 127 volt. The impedance is 13.7, and the current is given as 9.27. Then for the third harmonic, the frequency will be 180 because it is 3 times that of the fundamental. The output voltage is 0 for the third harmonic because it is switching at 30 degree, and the impedance is 30, the current is 0. There is no voltage, so there is no current. For the fifth harmonic, the frequency is 300 hertz, and the voltage Vn will be 25.5. How you calculate Vn? Vn we calculate as 4 VDC upon 5, it is fifth harmonic, into cos of 30. So from here you calculate this as 25.5. And Zn you calculate as under root R square plus N omega naught L square. You calculate Zn. And then In is what? Vn over Zn. Vn over Zn, you calculate this current. Similarly for 7th harmonics, similarly for 9th harmonics, and for 11th harmonics. So now we know these currents, then you can use the formula of the RMS values. So you see for the harmonic is fifth harmonic, so it is the 0.53. These are the peak values. These are peak values. So you divide by root 2 to get the RMS. So 0.53 divided by root 2 square, 0.27 divided by root 2 square, 0.11 divided by root 2 square. divided by 9.27 by root 2. This is the fundamental RMS. So what you get is 6.6% total harmonic distortion, which is less than 10%. So that means your design is correct. So this is how we solve. This is very important type of problem that you can face in the exam. So let me repeat this once more, summarize. So it says that design an inverter with supply of that will supply a series RL load of 10 ohm and 25 millihenry. Fundamental frequency is 60 hertz. That was actually given in the previous example. And the fundamental current is 9.27. And it says that the total harmonic distortion should be less than 10%. So we calculated the fundamental voltage peak value, and from there we calculated the DC link voltage. So the DC link voltage, the input voltage to the inverter should be 116 volt, and then corresponding to that we have calculated the 5th harmonics, 7th harmonics, 9th harmonics, 11th harmonics, and then we calculated the impedances, then we calculated the current, and then we calculated the total harmonic distortion in the current. So we see that it is less than 6.6%. That means it is fine. Now you can check that. If what happen if you consider only up to 7th harmonics, maybe it is less than 10%. Then you can stop at 7th harmonics also. That's not big problem because we are within the range. Okay. But suppose if it is still more, then you can go for one more harmonics. But up to 11th or 13th is enough for the calculation. Not more than that it will be required. Okay. Any question here?
Doctor?
Yes.
As for the exams, like we're not going to consider up to 7th, up to 5th or 3rd. No, up to 3rd should be enough, right? Since
No, third is already 0. There is no third is 0. 5th, 7th, 5th and 7th, and you check if the total harmonic distortion is less, then it's okay. You can just show up to 7th harmonic. But they have shown up to 2 more harmonic because 9th is already 0. So 7th, 1 more harmonic, 11th harmonic they have considered. But even if you say show up to 7 is okay, I have to check what is the answer if you just have those up to 7th. Check if your harmonics is less than 10 or not.
Good.
Next is the pulse width modulation. What is pulse width modulation? So you see the output what we have seen is only like square wave. So square wave means what? This is your half by t by 2, and this is your t. So the total period, in the total period, you have only 2 pulses. One is the positive VDC and the negative VDC. This is what you get in the output. So this is a square wave, and you see that the total harmonic distortion is very high, is 48.3% in the voltage and 16.6% in the current. So to reduce this harmonic voltage, what we do that instead of having one big pulse, what we do that we divide this into small pulses. We divide this into small pulses. Divide them into small pulses. So this square wave into small pulses, we are able to control the output voltage magnitude. We will be able to control the output voltage magnitude and the total harmonic distortion or the harmonic content. We'll see that we will be able to control the harmonic content, and we'll be able to also control the output magnitude. We'll also be able to control the frequency of the fundamental frequency. So we'll be able to control these things. So the output voltage magnitude, output fundamental frequency, the total harmonic distortion, the harmonic content, all these can be controlled, and if we use the pulse width modulation. So what we are doing that we are just changing the width of the pulse. So the pulse width we change, that we call it pulse width modulation. So pulse width modulation is a very important technique to reduce the harmonic content in the output voltage, to control the total harmonic distortion, to control the voltage magnitude, output voltage magnitude fundamental, and the fundamental frequency. Now, how we do that and what the different types of PWM, that we will discuss. So PWM concept can be applied for fast switching devices, because you see you have to have many pulses in half period, and then in the next half period. Now what we have seen that when you had square wave, the switching frequency was equal to 1 by T, which is equal to fundamental, which is equal to the fundamental frequency. Say, for example, 50 hertz. So the switching was only 50 hertz, and when you are having a square wave output, when you have a square wave output. So for a square wave output, you see, we have in the positive half cycle you have plus VDC, then in the negative half cycle you have minus VDC. So what does this mean? This means that this from entire this duration, your switch number 1 and your switch number 2 was on for half. So it was just on, kept on for half period, and then for the next half period in the negative half cycle, to obtain negative half cycle, we just on this and we on this. So that means there will be only one switching in one period, and you see it turns on here and turns off here. So this is for S1 and S2, turn on, turn off, and then turn on and turn off for the S3 and S4. So this is equal to the fundamental switching frequency. So the switching frequency means at what frequency it switch, it is same as your fundamental frequency. One on and one off in a whole period. So you have very less switching losses, because the switching frequency is very big. It's 50 hertz. But now when you are using PWM technique, you are switching it many times. It can be like, a 5 kilohertz switching, 10 kilohertz switching. And now with the new devices, silicon carbide and gallium nitride, we can have 100 kilohertz switching, 150 kilohertz switching, even 200 kilohertz switching. So very fast switching you can do. And as fast switching as you do, as many number of pulses you get in the half period and next half period, the better quality waveform you will get. The harmonic content will be reduced and reduced and reduced, and with the increase in the switching frequency. But certainly the switching losses will increase when you increase the switching frequency. So you have to have a trade-off between the switching frequency and the quality of the output voltage and output current. So very high switching frequency leads to reduced component L and C values, and those the filter that you will use along with the inverter. Also the devices, then it will have more switching losses. Now you see the silicon devices, the normal devices, we do not switch them more than 20 kilohertz. But if you have silicon carbide and gallium nitride devices, you can switch them at very high frequency, 100 to 200 kilohertz. So very high switching frequency, it gives you very good waveform. So PWM technique is an old and proven concept and has been used in industry since early 1960, especially for variable speed motor drives applications. MOSFET, BJT, IGBT technology has made it possible to use PWM techniques because they are high switching frequency devices. They switch at very high frequency, unlike thyristor, which switches at low frequency. The amplitude of the output voltage can be controlled with the modulation signal or the reference signal, sine wave of the desired fundamental frequency. We will see how next. The output waveform has lower total harmonic distortion. The two most popular PWM techniques, they are called sinusoidal carrier-based PWM technique. One is called, actually you call it carrier-based PWM technique, carrier-based PWM technique, or you simply call it sinusoidal PWM. Sinusoidal PWM. So sine or only sine PWM. This is one PWM technique. Another is space vector PWM technique. We will discuss sinusoidal PWM technique So in sinusoidal PWM technique, what you have? What do? You have a very high switching frequency triangular carrier wave, triangular carrier wave, triangular carrier wave, and you compare this with a sine wave. You compare this with a sine wave. The sine wave, we call this sine wave as modulating signal. We call it modulating signal, or we call it reference signal. So the modulating signal or reference signal. Since the modulating signal is a sine wave, modulating signal is a sine wave. Hence, it is called sine PWM. Hence, it is called sine PWM. So, sine PWM technique, or simply call it carrier-based PWM technique. Sometimes it is called carrier-based sinusoidal PWM technique. So, this is what you do, that you compare the sine wave with a triangular carrier signal, and you generate the base signal or the gating signal by comparing these two signals. So you compare modulating signal with the triangular signal, and you generate the switching signal for the switches. You generate the gating signal or the switching signal for the switching device. So whenever you see in this interval, your sine wave is more than your carrier magnitude. So in this case, you produce a high voltage or a high signal. You produce a high signal. And in this, I have to draw it more clearly, because just I show you a small cycle. Okay. So you see here, from this interval to this interval, the sine wave is greater than your triangular wave. So in this interval, we generate a high pulse. We generate a high pulse. Then in this interval, the sine wave is less than the triangle. We produce either zero signal, sometimes we produce maybe negative signal. Then in this, we produce high signal. Then in this, produce low signal. So these pulses, these are called PWM pulses or switching pulses. These pulses are given to the gate of MOSFET or IGBT, or base of the BJT. So the switch will be on when it gets the high signal. The switch will be off when it will get the low signal. So high signal means level 1, zero signal, level low level. This is high level, low level, high level, low level. So when it is high level, the switch will be on. The switch will be on, and when it is low level, the switch will be off. So there will be fast switching. Now, how many number of times it will switch? What will be the switching frequency? That depends upon what is the frequency of this triangle. The frequency of the triangle or carrier signal decides the device switching frequency. If it is 5 kilohertz waveform, the switching of the device, IGBT or MOSFET, will be at 5 kilohertz. If it is 20 kilohertz waveform, the switching of the device will be 20 kilohertz. Okay, this is one thing. The other thing is that the relative magnitude of this sine wave and the triangle wave, that decides the output voltage magnitude. That decides the output voltage magnitude. So the ratio of the amplitude of the sine wave and the amplitude of the triangle, we define it as a modulation index. We call it modulation index. We define as modulation index. So modulation index we define as the triangle magnitude over the or amplitude or the amplitude of the sine wave. The ratio of the two defined as the modulation index. So if the triangle is same as the sine wave, the modulation index will be 1. So the maximum value of the modulation index will be from 0 to 1. The maximum value will be less than equal to 1. So when the output voltage magnitude will be maximum when the modulation index is 1. Generally, we keep the modulation index from 0.8 to 0.9. Okay. So sinusoidal PWM technique requires a modulating or a reference signal of fundamental frequency. Okay, yeah, the frequency of the modulating signal defines what is the frequency of the output voltage, actual output voltage. If the modulating signal is at 50 hertz, the fundamental frequency of the output voltage will be also 50 hertz. If you want your output fundamental frequency to be 25 hertz, then you have to keep the frequency of the modulating signal 25 hertz. So just by controlling the frequency of the sine wave, you can control the output voltage frequency. By just controlling the magnitude of the sine wave, you can control the magnitude of the output voltage. So magnitude of the output voltage is controlled by controlling the sine wave magnitude, and the frequency of the output voltage is controlled by fundamental frequency of the fundamental frequency of the output is controlled by controlling the frequency of the modulating signal. So modulating signal is 50 hertz, the output voltage frequency will have 50 hertz. Fundamental. If the sine wave is 25 hertz, the output fundamental will be 25 hertz. Do you understand this point?
Doctor?
Yes.
I'm sorry, could you please repeat the part about the frequency again? Only the frequency.
Yeah, okay. So you see, the frequency of the sine wave, decide what will be the frequency of the output fundamental. Because you see, output is not pure sine wave. Output is like switched wave form. Output will be in this form. Or output will be in this form. This is your output voltage. A square wave output, or you will have this kind of output. Okay, switched wave form you will have. It is not a pure sine wave, but when you take the Fourier of this, if you take the Fourier of this, it will have a fundamental component and it will have some harmonics. The harmonics will be lower than what you get in the square wave, but still you will have some harmonics in it. Now the harmonic content, we are not bothered about that for now. What we are bothered about is what is the fundamental frequency of the fundamental wave. So the fundamental frequency is decided by the frequency of the sine wave. If the sine wave is of 50 hertz, the fundamental component of the output will also have 50 hertz. This is what I mean. Do you understand?
Oh, yes, doctor. Okay, clear. Thank you.
Now, there are two types of PWM. One is called bipolar. Another is called unipolar. Now, both these are implemented differently. They have different harmonic spectrum. Harmonic spectrum is different. Now, what is the meaning of bipolar? Bipolar means your output will be like this. It will be minus VDC plus VDC. Minus VDC plus VDC. This is how your output will be. Output voltage will be having plus VDC and minus VDC, plus VDC, minus VDC. So it is varying between plus VDC and minus VDC. Okay. So this is how the output voltage waveform looks like. This is called bipolar. Why it is called bi? Bi means two. Polar means pole. And this is one pole, this is another pole. So plus VDC, minus VDC, plus VDC, minus VDC. This is what you get in the output voltage. And if you see how we generate the gating signal, we generate gating signal when the sine wave is high. When the sine is greater than the triangle, you get high voltage. When the sine is less than triangle, you get low voltage. So in this instance, I get plus VDC. And in this instance, we get minus VDC. Actually, this will be the shape. This is the same shape of gating signal. Here what is shown is the output voltage. This is the output voltage. This is shown as the output voltage. Control is not shown here. Control is not shown here. But what I mean to say you that you see, this is exactly what you will see in the output. Your output will be whenever your sine wave is more than the triangle, your output voltage will be plus VDC. Whenever your sine wave is less than the triangle, you will have minus VDC. This will be the output. But how you are going to generate this? So you are going to generate this in this way. Let me show you. You have to have a comparator. Say, for example, an op amp. Here you give the triangle wave. No, this triangle wave should have the same switching frequency as that of your switching frequency you want to decide for your switch. Say, for example, 5 Hertz. So the period of this triangle should be 5 kilohertz. And here you give a sine wave. You give a sine wave. And the frequency of this sine wave should be same as what you want the fundamental output. Okay. And the magnitude of this we keep as +1 and -1. And the magnitude of this we keep as +1 and -1. Okay. This is for the control side I am telling you. Now what you get here is the waveform like this. By comparing the sine wave and the angle wave. This you give to the, after certain amplification, you give this to the gate of the switch, the power switch. Okay. Now you see at the output we get the voltage. This voltage will be same as this. Like this is your output voltage, actual output voltage. Okay. And what you get here is the gating signal. When the gating signal is high, your switch is on. When the gating signal is low, the switch is off. So when it is on, you get plus VDC. When it is off, when it is on, you get plus VDC. Sorry, zero. When it is, can you please mute? Somebody is not muted. Okay. So the thing is that this is how we get the output voltage. Now you see this output voltage, like it is like somehow sine wave. If you approximate this, you will see this will look like a sine wave. This is the fundamental component. This is the fundamental component. This is the fundamental component. So this is called bipolar switching. And whenever you have bipolar switching, what is the issue here? You see, your output is plus VDC, then minus VDC, plus VDC, then minus VDC. Who is not muted? Please mute.
Please. Hello.
Abdullah Al-Khali. Okay. So this is how the output voltage looks like. Now it has the output voltage as plus VDC, minus VDC, plus VDC, minus VDC. Now what is the issue here? That your switch stress is high because the change in the voltage dV by dt across the switch is VDC minus of minus VDC by delta T. So it is 2 times VDC by delta T. This is the dV by dt across the switch. dV by dt across the switch, because you are getting from plus VDC to minus VDC. So it is 2 VDC by delta T. This is the problem with the bipolar switching, because you have very high dV by dt, 2 times VDC. Okay. So you get output as plus VDC. When your sine voltage is greater than your triangle, you get minus VDC when sine is less than the triangle. So S1 and S2 are on when your sine wave is greater than the triangle, and you get plus VDC as your output. So whenever your sine wave is more than the triangle, the switch S1 is on and S2 is on. So at the output, what you get is plus VDC. When your sine wave is less than the triangle, then you get minus VDC. By switching on S3 and S4, you get this as your output. So this is PWM, pulse width modulation, bipolar. Now another is called unipolar PWM. So in the unipolar switching, what you get, your output you get like this: plus VDC 0, plus VDC 0, plus VDC 0, plus VDC 0. Then in the negative cycle, negative VDC 0, negative VDC 0, negative VDC 0. So it only varies. It goes from plus VDC to 0. Then in the negative cycle, it goes from minus VDC to 0. Okay. So what is dV by dt in this case? VDC by delta T. So the dV by dt is low in the case of unipolar switching. In case of unipolar switching, okay, this is how you see the output voltage waveform. So output voltage waveform, again, this looks like sine wave. The fundamental sine wave will be fundamental will be sine wave. Then you have harmonics, but here in the bipolar, you had plus VDC, minus VDC, plus VDC, minus VDC. Here you have plus VDC 0, plus VDC 0, then you have minus VDC 0, minus VDC 0. Okay. Now, how you generate this? You generate this by comparing two sine wave with the same triangle. Two sine wave with triangle. Triangular carrier. Two sine wave with same triangular carrier wave. So the carrier wave is high switching frequency, 5 kilohertz, 10 kilohertz, 20 kilohertz, like this. And what is the frequency of the sine wave? The sine wave frequency is the same as the output fundamental frequency. The output fundamental frequency is 50 hertz, then the sine wave should have been also of 50 hertz. Okay. Now, what you do that, you have the triangle, this is your triangle, and you have one sine wave, one modulating signal as this, and another modulating signal you have this. So you have two modulating signals. Okay, you have two modulating signals. Okay, so you generate two set of pulses, one by comparing plus VDC plus sine, like the sine wave number 1, and this is sine wave number 2. So you compare sine wave number 1 and triangle. This is one set. The another set is sine wave number 2 and the triangle. So we generate two set of pulses. So this is for positive, this is for the negative. Okay. So when you just look at the positive, this sine wave, you generate this as your pulses. This is called VA. This is your point A. So this is VA. So that means this pulse will go to S1 and S4. And this pulse goes to S3 and S2. So this pulse, when you compare the negative one, when you compare the negative sine wave 2 with the triangle, sine wave 2 with the triangle, you generate these pulses. You generate these pulses. You generate these two pulses. Okay. So S1 is on when sine is greater than triangle, and S4 is on when sine is less than the triangle. So when the sine is greater than triangle, S1 is on. S1 is on. So S1 is on when sine is greater than triangle, and you get VDC as your output. When S4 is on, sine is less than the triangle, you get 0 as your output. So when this is on, you get this voltage as plus BA. When this on, you get as 0. Here, when this is on, what you get is plus VB. This is point B. When this is on, you get your 0 as your VB. So voltage across this, we call it VAB, which is equal to VA minus VB. VA minus VB. So S3 is on when negative sign is greater than triangle. S2 is on when negative sign is less than triangle. So this is how you generate the PWM signal, by comparing the positive sign with the triangle, comparing negative sign with the triangle. When you compare positive cycle with the triangle, you generate the getting signal for S1 and S4. Okay. When it is high, when this is high, this will on. When it is low, this will on. So here at this point, S1 on. At this point, from here to here, S4 is on. Similarly, for the negative cycle, you generate this from sine triangle from sine triangle comparison, the sine 2 and triangle comparison, you get this as your signal. When it is high, S3 is on. When it is low, S4, S2 is on. So this is how you distribute the gating signal. Any question here?
All clear, Doctor.
Now there are some terminologies that are used in the PWM. One is called the frequency modulation ratio, another is called the amplitude modulation ratio. This amplitude modulation ratio also called modulation index. Frequency modulation index is defined as the ratio of the triangular carrier wave frequency divided by the frequency of the sine wave. So if the triangle is say 5 kilohertz and the sine wave is 50, then you have 100 as your frequency modulation ratio. This is defined as the modulation index or only modulation index or amplitude modulation ratio. We define as the sine wave over triangle wave. Okay, so this is sine over triangle. So if the sine is 0.9, this is 1, then it will be 0.9. If both are equal, you will have 1. So the maximum value of MA or modulation index is equal to 1. For MA less than equal to 1, the amplitude of the fundamental frequency of the output voltage is linearly proportional to MA. So the fundamental output is given as modulation index times VDC. Now we'll discuss the harmonics in the PWM. So how the harmonic frequency looks like in the spectrum. So you see in the square wave, if we have only square wave output, the harmonic spectrum is like this. You have fundamental, then you have third harmonic, then you have fifth harmonic, then you have seventh harmonic, like this. But in the PWM case, it will not be like this. The lower order harmonics will be eliminated. And what you will see, the spectrum is like this. At fundamental, then you will see at the switching frequency. At 2 times switching frequency, 3 times switching frequency. So this is how you will see the spectrum. So there is no low order harmonics. The low order harmonics 3, 5, 6, 7, all these are eliminated. They will not be there in the spectrum. So the Fourier series of PWM output has a fundamental frequency component which is same as the reference or the modulating signal. Modulating signal is sine wave. Harmonic frequency exists at and around the multiple of the switching frequency. So the switching frequency is suppose 5 kilohertz, then your harmonics will be around 5 kilohertz, multiple of 5 kilohertz, 5, 10, 15, 20, like this. At those frequencies it will be available. The magnitude of some harmonics are quite large, sometimes larger than the fundamental. So this sometimes become large, even more than the fundamental. However, because these harmonics are located at high frequency, a simple low pass filter can quite be effective in moving them. So you need a small filter to eliminate this. Small filter. Okay. So this is the harmonic for the PWM. So this is normalized frequency spectrum of a bipolar switching. Considering this frequency modulation as odd integer. MF is F triangle over F sine wave, and say this is odd integer. And the modulation index, amplitude modulation index, or simply modulation index is 1. That means it is operating at 100% modulation. Then the harmonic spectrum will look like this. You will have a fundamental, it is normalized, so it is 100%. It is like 1 per unit. Then you will have at MF 2 mf, 3 mf, 4 mf, like this. Okay. Suppose your frequency is 5000 and your sine wave at 50 hertz, then you will have 1000. This as 1000. So this is at 1000. This is as 2000 hertz, 3000 hertz, 4000 hertz, like this. Okay. And these are the Fourier coefficient Vn by Vdc for bipolar PWM. So this is for n is equal to 1, means fundamental. For modulation index 1, the Vn by Vdc is equal to 1. Vn by Vdc is equal to 1. For 0.9, it is 0.9. For 0.8, 0.7, 0.6, 0.5, 0.4, 0.3, 0.2, 0.1. This is for fundamental. Now, for n is equal to mf, mf means mf harmonic. So, for example, here it is 100 harmonics. mf is equal to 100. So, this is 100th harmonics. 100th harmonics, the magnitude is 0.6. You see, this is 0.6. If your modulation index is 1, it will give you 0.6. If you use 0.9 modulation index, it will be 0.71. If you use 0.8 modulation index, it will be 0.82, and so on. Then this is another harmonic component, 100th plus minus 2, means 98th harmonic and 102nd harmonic, 102 harmonic. The magnitude will be 0.3 and 0.27, 0.22, 0.17. Please tell me if you understand this table or not, because this is used for the numerical example. You have any question here?
No clear, doctor.
The x-axis shows the harmonic number. The first dominant switching harmonics appears at n is equal to mf. It appears at n is equal to mf. And its sideband. Sideband means this is your at mf. And then mf plus 2. This is at mf minus 2. Side bands are mf plus 2, mf minus 2, then mf plus 4, mf minus 4, and so on. Next dominant harmonic appears at 2 mf. It appears at 2 mf. So the harmonic will be at mf, 100th harmonics, then it will be 200th harmonics. Then here it will have big, then it will have side bands, symmetrical, side band, symmetrical, like this. This is 2 mf. This is 2 mf plus 2. No, 2 mf plus 1. 2 mf plus 1. 2 mf plus 3. This is 2 mf minus 1. This is 2 mf minus 3. This is mf. This is at mf plus 2. This is at mf plus 4. mf minus 2, mf minus 4. So this is how the harmonic component. This is the harmonic component. The switching harmonic exists at multiple of. The switching harmonics exist at multiple of switching frequency. We'll see that. So this is with respect to the ratio mf. mf is what? F of carrier over f of sine. This is here, it is shown switching frequency. So the switching frequency say 5 kilohertz. So this will appear at 5 kilohertz, then 5 kilohertz minus 2f1 plus 2f1. What is f1? Is say 50 hertz. So it will be 5 kilohertz plus 100. 5 kilohertz minus 100. These are the two, and so on. 2 MF, there is nothing. You see, this is absent. 2FC is absent. But you have only sidebands. You have only sidebands. So this is with respect to switching frequency. This is with respect to frequency. And this is with respect to MF. The ratio of the switching frequency versus over sine wave. Now this is an example. It says that the full bridge inverter is used to produce 60 Hz voltage across a series RL load using bipolar PWM. The DC input to the bridge is 100 volt. Amplitude of modulation ratio MA is 0.8 and the frequency modulation is 21. So 21 means a F triangle or F carrier over F sine wave. This is given as 21. This is equal to 60. So you can calculate what should be the frequency of the triangle. Frequency of the triangle should be 1260 Hertz. The load has a resistance of 10 ohm, inductance of 20 millihenry. Determine the amplitude of 60 Hertz component of the output voltage, means fundamental component. What will be the fundamental component of the output voltage and the current? And then power absorbed. And the total harmonic distortion. So what is the fundamental output? Fundamental output is given as MA into VDC. This is how you get the fundamental output. So fundamental output is 0.8 times 100, 80 volt. The current is given as Vn over Zn, where Vn upon under root R square plus N omega naught into L whole square. So for the fundamental current, this will be 80 over under root 10 square plus 2 by 60 into 0.02, that is inductance value. So it is 6.39 ampere. This is fundamental. Next, what will be the next harmonics? So you see, this is fundamental. The next will be harmonic is MF. And after that, the next harmonic is this. So MF harmonic. So MF, what is the value of MF here? Given as 21.
21.
So what will be the harmonics? This is fundamental. MF, MF minus 2, MF plus 2. You see here. MF, then MF plus minus 2. So MF plus 2, MF minus 2. So MF minus 2 is 19 and MF plus 2 is 23. What will be the frequencies? 60 Hertz. This is 11 times 19 times 60, 21 times 60, 23 times 60. What will be Vn?
MA times
Yes. So MF20, the first harmonic is at 21, 19, 23. U stable 8.3. Yeah, you see V21. How we get V magnitude of V21? So this should be equal to V21. We have to look at this table because the modulation index is given as 0.8. Modulation index is given as 0.8. So for 0.8, MF is 0.82, 0.82. Fundamental as at 0.8 is already calculated. MF is 0.82 and MF plus minus 2 should be 0.22. So you see here, this is 0.82
Doctor,
6.22. Yes.
I believe we do have quiz in 1 minute.
Sorry.
We do have quiz in 1 minute.
Oh, you have quiz. Okay, I forgot. Okay, sorry. Okay. So I will stop here. We'll continue with the same problem. Okay. And let me check. Sorry, I completely forgot.
It's fine.
Okay, I will stop now recording, and then I will be online. If you have any issue, I can